Well, I'm back. As you can see, I have final exam here. This is not a final exam with solutions. Now, so this morning what I did is I went through the two midterms, also no solutions. And I was hoping to get a kind of sense for how well I would do in them. Unfortunately, I think my difficulties here are often, I think if you have a class that is you're feeling extremely confident on, or you're feeling extremely bad on, you can kind of tell in the exam, right? Like, I can't even answer this question versus I'm getting all the questions right. And so I'm kind of in the middle range. So I think this is the situation where an exam without a solution is just going to be a little vague. I did try to estimate it on the first midterm because it was a little more clear cut which questions I got right, which questions I wasn't sure about. Whereas in the second midterm, I just went over and I just couldn't do it, because even the ones that I felt confident about, there's a chance that I made a calculating mistake. And some of them I didn't feel quite as confident about, but I still felt like there was a reasonable chance that it was right. So it's really just, unless someone who knows something or has enough quantum physics knowledge who can grade those exams can come in and, point out what I did right or wrong, then, that's just all we'll have to leave it at. And today I've got the final exam. Again, this is from the session of the class that I actually took. I did double check. I do think I have a final exam that has solutions from another session. The reason that I'm doing these exams, which don't have solutions, is, first of all, I wanted to get a kind of feel for how hard these final exams are for this particular class. I know I'm not getting graded on it, so it's not exactly fair. It's not exactly like, I can't really say, oh, I passed it, because I don't know what the solutions are, right? So I'm not going to be able to do that. I'm not going to be able to do what I did in the MIT challenge, at least for this session. On the other hand, the exam, I think it's a practice final exam for a different session, and I want to say it's from an earlier session. So I think this is 2000. This one says 2012, but I think I was doing the 2013 sessions. This was just 1 year before, but same professor, so probably should be the same. And so this one was an example of, okay, the exam is, the exam matches the class. The other one is from, I think, I don't have it. Well, let me see. I might have it in my, I might have it in one of these folders. I could say which. I think, yeah, so it's from 2010. And let me just see if I have the list of the professor. Vuletic is, yeah, Vuletic. So I haven't looked at that exam, so I can't say what it's going to be like. It may be pretty much the same as this exam, in which case, great, I can do it and I can kind of grade it and get some sense of how well I did through this class. On the other hand, as I said, I haven't checked it, so there's a possibility that it will either ask questions that are broadly similar to the ones that are in the class, but maybe phrased in a way that if I had taken that session, I'd understand the phrasing, but not on this one. So there's just little examples of that, like differences in notation. I had one of these examples in the MIT challenge where I did a signals and systems class, and they did everything with these diagrams, which they weren't covered in the session I was doing. And the entire exam was drawing these diagrams. And I was like, I have no idea how to draw these diagrams. So that one, I just, okay, failed this one. I have to go do a different one. Now, luckily, there were a bunch of exams for that class, so I could just do a different one. But for here, I've just got the one. Just got the one with solutions. And as I said, it's from a class. Did I just say it was 2010? Yeah, so it's a few years earlier with a different professor. So I'm hoping it's going to be similar. If it's not, obviously, I'm going to just have to sort of see how I want to look at that if it doesn't match the curriculum I did. Now, this has definitely been a hard class for me. I've mentioned this sort of from the beginning, that I knew it was going to be a challenging class. I kind of picked it because I wanted to take on a hard class. Live streaming, I just figured, what's the point of doing a class that I'm going to find easy doing a live stream? It'd be more interesting to do a class that I find challenging and sort of, show how I handle that. But on the other hand, the converse of that is that when you take on something that's challenging, it could be too challenging and you could fail at it. And so there's a reasonable chance that I'm going to spend this whole month working on this, and I'm not going to have reached the benchmark that I wanted to reach. I don't think that's a real problem. I mean, this is a little bit arbitrary what I'm setting out. This is not me being an MIT student having to pass an MIT exam in order to get a grade. So, you know, I've learned a lot in this last month, and if it wasn't enough to pass this exam, it's still a lot more than I knew beforehand, and it still goes towards my overall goal of getting a deeper understanding of quantum mechanics. If it wasn't quite enough to pass this, just means that I need more practice. It means I need to understand more of the calculating techniques. It means that I need to dig deeper. And if I keep working on it, I'll eventually get there. So on one perspective, it doesn't really matter. You know, I feel like I've put in the effort to learn this. On the other hand, though, part of the reason for doing this was also to show you what you might do in such a situation when you're facing a really challenging class and how you might study for it. So obviously in that case, if I were an actual student and I failed the exam, well, I got to take the course over, or I've got to do something like that. So as I said, this is, you know, it's always a little bit of a risk when you take on these kind of projects that you might not have the difficulty calibrated. I was lucky with the MIT challenge. In fact, in the MIT challenge, I had a bit of the opposite problem. I took some of the earlier classes and I did them in a compressed version of time, and I was like kind of on the edge. And it just turned out that not only well, I had extra time because of the way I scheduled it, but also some of the earlier classes were some of the ones I found harder. Once I got deeper into computer science, the more computer sciencey classes I found easier, and I was able to push through that way. Another example would have been when I was studying Spanish in Spain, that I had this whole idea that, you know, well, maybe by the end of 3 months, barely I'll be able to, like, you know, have conversations and stuff. And that was more like something that happened at month 1, like not fluent, of course, but at a level where it was very comfortable to live there for most of the time. It was pretty relaxed, and I was, you know, I felt interacting pretty well with people. In contrast, when I was in China and Korea, it was much harder. And so I was expecting the difficulties to be like one was going to be a little bit harder than the other, but it turned out that probably learning Chinese is more like 3 or 4 times as hard as learning Spanish. So there's always these calibration difficulties. And then for this class too, it was a little bit like that. I hadn't done all the prerequisites, and the ones that I had done years ago. So I think I spent a lot of this month really kind of reloading a lot of old knowledge, like getting reacquainted with calculus, multivariable calculus, differential equations, linear algebra, you know, even just classical mechanics, electromagnetism. All of these things have had to been kind of refreshed a little bit, and I've also had to learn some stuff from the class that I missed. So in this sense, it's definitely been challenging, and it's definitely been the case that regardless of how these exams go, regardless of whether or not this is something that, you know, I can say, give myself a thumbs up and say I passed, or whether it's something where it's like, well, I don't think that I met the benchmark that would have qualified for an MIT student in this situation. I still feel like I've learned a lot, and I still feel like I've pushed it forward. It's a little disappointing that I don't have more of these final exams with solutions, because I would have done more earlier, I think, and I would have tested myself more frequently. Instead, I just had the problem sets, which I'm even seeing from doing the midterms. They're just different from the exam, because the problem sets were like very heavy on calculation, whereas these are much more conceptual. But at the same point, not to say that, you know, obviously doing the problem sets helps with these as well, but if I had had more of these exams, I might have focused my energy a little bit differently. That's just sort of how it is. I don't really think there's anything that could be done about that. So what I'm going to do now is I'm going to work through this exam, which I guess I'll just switch the view here so you guys can see me doing it. I'll switch to the exam, which I don't have solutions for, so that I don't have anything to grade this after, but I will get a kind of qualitative sense of what the final exam would have been like for this class, even if I can't evaluate myself on it. So I'm going to set a timer. It's a 3-hour exam. Try to work my best through it. Once I'm done, I'll have some sense of this exam, and then I can do the final exam for the other class, the other one that I have. I'll try to do that tomorrow morning. Again, doing the midterms, I feel like again, it's really hard to guess, because I've done these classes before, and I've found that unlike the computer science classes, with the calculus heavy classes, it's a lot easier to make little mistakes. So it's a lot easier to, forget a minus sign or, put something in the denominator when it's supposed to be in the numerator. And I mean, as you get better, these mistakes become less common. So I don't want to say that, mistakes don't matter, but it does mean it's a little bit harder to self-check because the actual answer is going to be some complicated thing. It's not going to be like yes or no or something like that you should know fairly easily. So I think I'm gonna go through this exam right now. I'm gonna cover up the chat. So while I'm working on the exam, I won't be responding to chat questions. I won't be looking at chat questions, so that there's no way for you to communicate with me while I'm doing this. Obviously, I'm gonna be leaving my computer open because I have to run this live streaming software. But otherwise, this is gonna be pretty close to how one would do an exam at MIT. And so I'm looking here. Doesn't look like there's any things. Oh, I need my formula sheet because that was a separate document. And I printed it off already. So this formula sheet I'm quite used to because I've been using it for the last little while. And I've got some spare paper up here too. But, oh, there we go. So, I guess now's a good time to start. I'll set my timer for 3 hours. And then I will begin. Oh, you know what? Let me sharpen my pencils first. I've got a couple dull ones here. 3-hour exam. I don't want to be taking breaks to sharpen pencils now. All right. Okay, let's set a 3-hour timer. So that's going to be roughly 4:08. I should be finishing just if I want to look at the clock. Or let's say 4:10. I'll give myself an extra 2 minutes. Okay. All right. What is the date today? It is April 29th. Okay. Degenerate. Two slit interference patterns. Curve in the Banach closage computer. To be even qualitatively correct. Okay. Probability density. All right. Ooh, lattice spacing. right. Okay. All right. Circle each correct statement valid for all eigenfunctions. Well, this is true. May be chosen to be even or odd. No, this is not symmetrical. Circle each correct statement for V naught less than E less than 0. So E naught is here. Discrete. Degenerate. I would say no, not exactly degenerate, because you've got like, yeah, it's not exactly degenerate, it's nearly degenerate. I'll leave that blank. I would say that it is not discrete. Degenerate, no. I would say no for all of those too. Floor 2 slit interference pattern generator setting 8, 270,006 lambda through 20 minutes. Center image D. If the maximum on the left is equidistant from both slits, on the left, is that this here? No, this is equidistant on both slits. This is 1, 2, 3.5. By means of errors, let's indicate the ways, or the way or ways qualitatively correct. Maximum. What other things are wrong about this? Tail should decay resistor here, and on the left-hand side, we have how many nodes? 1, 2, 3, 4, 5 nodes. This one is 4. This is higher and narrower. Should be lower. Is there anything else that's wrong about this? I think that's about right. Can't think of anything else. Particle of mass m moves freely along a circle of length L. Our exponent claims that the wave function may satisfy the boundary condition. Psi L is equal to minus. No, cannot doubly valued. Use the physical boundary condition to determine the energy eigenstates and eigenvalues for this system. What is the degeneracy of each energy eigenvalue? So we have psi of psi prime. States are the I kx would be 2 pi n and integers, right? Oops, on the next page. Degeneracy of each eigenvalue. Good question. What is the degeneracy of each eigenvalue? Degeneracy is equal to k squared k squared is equal, or k is equal to minus k. Degeneracy is 2. close enough. All right. Sketch the probability density for the energy eigenfunction corresponding to a particle incident from the right. The potential below. We're going to have what? E ikx. So this is right-hand side, left-hand side, inside. And what's going to get eliminated? Well, our what is this? This is which one's going to get deleted? A to the E ikx. And this one's going to get deleted because it's incident on this direction from the right. So assuming wave packet, so it's normalizable, we're going to have something like energy eigenfunction. I guess, okay, so for an energy eigenfunction, it's going to be something like this. Choose two non-interacting particles which are placed in the same potential Vx, whose single particle energy function. So I'll go, this is boson is going to be equal to R, so they're the same energies. Not possible for this fermion. right? Diamond has a band gap, Eg equal to 5.5 electron volts. Lattice spacing A of the diamond lattice. Do we have periodic potential, any of those equations? I don't remember the formula. Rough estimate of the lattice spacing. So if the band gap is 5.5 electron volts, so that's from the low state to the high state. So we have, we have this. That means that the difference between what is the formula here for this one? All right, I'm just gonna, that one I have not done, so I'll leave that one here. It's the minimum wavelength which a diamond in a jewelry store is opaque. So we have 5.5 EV. How do we have that? Where's our H? Okay, so 5.5 EV. So can I answer that right now? No. Doesn't depend on the size of the diamond. Oh, if size. What is the minimum length which is opaque? 5.5 electron volts. So the energy of a photon is equal to equals h bar squared k squared. I don't think there's any m here. All right. I'm just going to leave it like this for right now. But I will have to go back to that question. Degeneracies in a 2D box. Consider particle mass m in 2D combined. All right, energy eigenvalues is going to be E0 is going to be equal to Oh, do I have the actual closed form? Where's the infinite well here? Another k squared here, so 0. I guess this is. What are we doing with this? This is not equal. Let's go. This one is going to be this one we have. So this is theta 0, theta 0. This is theta 0, theta 1. I'll go x, y, x, y. And we also have theta 1, theta 0. So d2, de0 equals, I guess, 1. E2, we're going to have no, it's going to be, because this goes up by a square, so it's going to be by a square each time, so it has to be 1, 1, right? T2 is equal to 1. So we have squared. This is going to be times 2. How about we got 2 of them? So this plus this. This is going to be 4. And then E3 is going to be 1, 2 plus 2, 1, 2 again. We're going to have first one is going to be 1 plus, so 2, 4 plus 3, 9. This is 5 plus 4 and 3 is 9. 4, 3 is... Modification, the side lengths will lift all degeneracies. Reduce but not eliminate the number of degenerate energies. Okay. Oh, one with hydrogen for at time equals 0. I hope I didn't get any of these questions. So that's this moment. At time t equals 0, an electron in a hydrogen atom is in the state. Determine A. So we're going to have 3 squared is 9 plus 16 plus 1 plus 10 is equal to 27 plus 9 is 36. So A is equal to 1/6. What is the wave function at time t equals this? So psi r naught t e t minus I e t over h bar. I don't know that I can do it that way. What do I want to do? I'll just add to each of them. Psi guess I can't do this because I'm not in an energetic state, so I want to do let's put this as A. What is the E for this? Is the hydrogen state? It's just based on N, right? N squared divided by 4. What is the, do we know what the energy is? Just put E to the I, E0. Put this right here, minus 4. Theta 2, 1, 1, 4. And then it's going to be E, not E1. E1, and this is going to be E2. What is the expectation value of E in terms of E1? All right. Equal to 936 E1 plus, what's the other ones? 416, 17, so it should be 27. E2, expectation value L squared, T equals 0. T equals 0, we have 0, 1, 1, so it's going to be L squared, H bar squared, is going to be equal to H bar squared, and this is 0. And then this one is 1, so it's going to be 27, 36. 27 over 36 times 1 plus 1, 2. Okay, expectation value L set at T equals 0. So we're going to have 936 plus 136 times 0 plus 1636 times 1 plus this cancels. 36 divided by 6, is this? 4 ninths. 4 ninths minus 2.5 ninths. No, whatever. Close enough. Which of E, L, Z is vary in the state? Time in this state. Oh, these 3. Because I should say phase. That's right. What is the shortest time? Time 0, which the spatial dependence of the probability returns to what? Oh, it's the ratio of E naught to I think it's n squared, so I think it's going to be so we have periodic in E 1 over h bar and E2 over h bar. So when this equals 2 pi and this equals 2 pi, right? And E2 over h bar is equal to n pi. I'll call this m2 pi. Probability density. Oh, probability density returns to what it was. Well, I don't know whether that changes anything. I don't know what the ratio is of E1 to E2. I want to say it's squared, so I want to see E1 times E2 over H bar squared. Is it 1 over this? What's the units? This is kilograms unit squared per second. This is joules, and this is joules second. It's the common factor, so it's not going to be this. Oh boy. 1 over second. It's the lowest common factor. What is that? Okay, I'm just going to put a little star here. Suppose that a measurement of LZ at t equals 0 yields h bar. After this measurement, what is the properly normalized wave function? R and t. Well, what is our? Do we have one that's a? E to the minus I e to. All right. Imperfect mirror. Consider the following attractive potential on the half line x greater than 0. Infinite less than 0. Negative v naught. Is it this way? No. 0 less than x less than L. L is less than x. Yeah, okay, it's just like this. What? Okay, suppose the potential has precisely two balanced states. Sketch with a corresponding wave function. So we're going to have I'll call this E naught. And E1. E1 is going to be like this. So this close to 0 means that this is going to be a very, very weak decay, which means that we're going to do something like, what are they going to look like? It's going to start tilting down right. Okay, right. Assume the second bound state is at threshold. What is the value of Z naught for this to occur? Ooh, 2ml squared V naught H bar squared. K is almost equal to, it should be 1.5. So L times, what is it, 3 halves pi, something like this. How can I get this Z naught? Put a star in that. What range of values of Z naught is consistent with precisely 2 bound states? So I have to do this graph again. It's going to be one of these guys. It's going to be like the one we had before. So it's KL is equal to, is it 3 halves pi? Did I do this the other way? So this is like pi by 2, pi 3, pi by 2. What range of values of Z naught is consistent with precisely 2 bound states? So this is where we get, so there's going to be 1 bound state always. And when are we going to get the second bound state? So we get one bound state when this is going to get the first odd bound state at 3/2 pi. When are we going to get, when is it going to appear? It's at 3/2 pi. Oof. Do I want to try to solve this, or can I guess at it? Yeah, maybe I should try to solve it. So what do we have? We have Z. Well, we're gonna choose odd. So right away we can get rid of this guy. And then on the outside, we can also ignore this one here. First order condition. All right, so now let's set it equals 0, B. No, that can't be right. What did I do wrong? B e to the I kx is equal to 0. this. Where did this guy get out of? There we go. What range of values of xenon is consistent with precisely 2 bound states? Z naught is equal to G naught squared. I can't for the life of me think about what the function was. I think it was something like KL. Something like that, right? Something like that. Where would the third bound state come up? Anybody likes this? 1. I don't know. That'd be my guess. Yeah. Consider non-energy eigenstate of positive energy E greater than 0 represented by a wave coming to the right and reflected wave so that x greater than L we have psi x. An ansatz? I don't even know what that word means. All right. So we have psi x equals I'll call these A. So B to the I have C to the IKX. So we know that this this corresponds to a rightward moving wave. So we can get rid of this guy. And so we have oh, wait. Oh yeah, we want the reflection. We need both. So let's say we can't get rid of this one here. Plus. So we got two of these guys, but we need to have another one. We're going to have a e to the I k prime x, b e to the minus I k prime x equal to 0 is at 0. So all right, what should your answer reduce to? V naught is equal to 0. Well, r squared should go to 1. This is going to go to e to the particle of mass m and a 1D harmonic oscillator potential with frequency omega. I'm gonna say psi. Okay. All right, specified psi t, which has do it with the operator method. We do some operator method here. What's the right way to do this with operators? I'll go t x. dt of all this is just going to have these guys drop down, right? Going to have the E operator, so it's going to be hold on a sec, we can do IH bar TDT. So if we get what is this going to be? Can we change this into operator somehow? Minus E IH bar 2. I think these guys are going to both be give me 0, right? It's just going to be these cross terms. Right? Expectation value x in this 0, this is 0. So this is going to be forgot the minuses. I think these actually cancel. Yeah, this should just be 0. And then this is going to be -0 and plus. So what are these two guys? both have the right number of terms. Guess we can raise one of them, lower one of them. Yeah, I'm stuck on this guy. All right, what's this one? What do you know about the quantum oscillation avalanche? Half harmonic potential. What is this one? Half harmonic oscillator potential. So let's think. This is going to be equivalent to the first odd state. 1/2 of that, right? Because it has to be the nodes in the middle. So the half harmonic oscillator on E0 is going to be equal to where's our harmonic oscillator? I think it's going to be 1/2. What are they? I think these are, so what is it, 1/2 h bar omega, 3/2 h bar omega, like that. So these are going to be 3/2 h bar omega. H bar omega. Consider a novel harmonic oscillator with the energy operator takes the form H bar omega A. What is our H dagger A plus 1/2? Okay. Oh, weird. Okay. So, oof. So we can commute this guy through as we have, let's go equals H bar omega squared and have A, I'll go A dagger A dagger A. I don't think I can do it that way. I go A dagger omega squared, A dagger. And I've got A dagger. And I can say this is equal to 1 minus A dagger A. This is equal to H bar omega squared. Dagger A. This is equal to 0, so this whole thing cancels, and we have A dagger A. Can we do anything with this? Oh, right. So this is equal to H bar omega E F. Okay. Show that there must be a state annihilated by alpha. Call this state phi 0. Okay. Phi gives us how can I demonstrate that there must be one here? This is probably best proof by contradiction. Go EF. So A of F is equal to H bar A. Um, yeah, I'm not sure how to do this one. Just have an A dagger. Is this a print here? Like, is there supposed to be an A dagger here? I don't know how that helps me. Yeah, I don't know whether that's true. No, everything else is displaying correctly. I think. What does it say? Cannot be annihilated by this. Oh, okay. So no, not deal with it. How do we prove this? Oh, I don't think I can answer that one. Still got quite a bit of time. So, do I want to go back up and look at some more questions, or I'll just keep working on this one, I guess. So we need to show that sure we got this right. Plus AA. Oh, right. Okay, this is how we're going to fix it. It's equal to A equal to 1 minus A. So we're going to have should be able to keep going, right? I think the counterfactual is that we could, if not, we can keep going lower and lower and lower, right? I'll use some sheet here. But we know this is also equal to a phi n. Let's try doing it this way. So if we have EF squared we showed that was equal to H bar EF. Oh, what are the possible eigenvalues? I forgot to answer that question. Possible eigenvalues of EF. So these are our eigenvalues and h bar omega. And how do we show that it has to be that way? What did I forget? How did that proof go for showing that? So EF is equal to, so EF theta is equal to E. Let's go. But it's also equal to h bar omega A of A. And if we go A, this one, what did we just work out? We worked out it was A minus this. So we have h bar omega A dagger A. So A dagger. And A. I think I already did this though, didn't I? Let's just look again at the top. So we have, suppose we have E. We also know that this is equal to h bar omega A dagger A phi 0, which we can get it equal to commute this one through. We're going to have what? We're going to have A dagger A. dagger A is equal to 1 minus E dagger phi 0 is going to be equal to H bar omega minus 0. So we have H bar omega A minus E 0 Oh, what am I doing wrong here? C. Let's try it again. Yeah, H bar omega. It does not equal this. Show that sigma cannot be annihilated by A plus A bar. What's the relationship? It's A dagger, A dagger, A not. Let's move it in. Do I want to move it in? This is not actually this. This is not right. It's going to be omega and there's going to be two states. Yeesh. Whether this holds. Not right? No. Man, this is a hard question. must be some kind of similar logic here. AW. What's our 1 minus? So that's 1 minus plus 1. Oh, this is minus. Oh, it's like minus. I think I gotta do it the other way. So we got alpha plus is 0. E alpha. I want to commute. What do I want to do? Commute this guy through here. don't want to do that, do I? I think I want to commute it all the way through. I want to commute it all the way through. So let's go. He has also. Get this through here. We get. I got to do the other way. So I got H bar omega. I don't know. I got to do it 1 minus A bar 1 minus A bar A. And then we have H bar omega. How do I commute it through the other side? Do I have any other commutation relations for? No. And how do I get this one over? I'm just flipping it back to where I started. How do I flip it through? I think I can go H bar omega A bar. H bar omega. This is. I can do. A bar minus. Well, at least I think I can do this part, because if we accept that definition, then a theta 1 equal to theta 0, and we have a bar theta 0 is equal to theta 1. Oh, all right. Let's see. I think this is all the. Oh, here we go. Verify the functions of EF and find their eigenvalues. I want to show this. How do I show that? H bar omega A. Oh, does it look right? How do I show that it gives me this theta 0? Oh. Equals H bar omega. This is eigenvalue 1. And H bar omega plus 1, I think. And then let's do the opposite. A dagger theta 1 is equal to H bar. is equal to lower to 0. All right. I'll put these guys at the end here. What are the ones that I want to go through? Oh, here we go. Lattice spacing A of the diamond lattice. Well, what did we figure for the band gaps, the way that they work qualitatively? The top of the band gap is it's approximately this one, right? Or like some Vx. This is the top of the lower band. Lower band. And then of the higher one, we're looking at no. It would be let's use our delta function ones. This is going to be our lower band, and then what's the next one up? So what's the approximate difference between these guys if this is this is still one node. It's got to be 2 nodes, right? What is it gonna look like? It's gonna look like this. Right, yeah, like this. So this distance is what? KL low 1 period in here, 1.5 periods in here. 1 period below 1.5 periods above gap. What's the energy difference? 5.5 electron volts. Can I calculate right here? Hmm. Um, so 2 pi over lambda. 5.5 eV times 2 mass an electron. Divided by h bar squared. All right. Oh, how do you calculate this? It's going to be pi. Lambda 1 divided by L. L1. That's going to be L divided by divided by 1.5 is 4/3. Yeah, 4/3. Thirds pi L K2. So we have 5.5 V is equal to H bar squared. Oops. Now I can't get the L. Ugh. What's the difference between these two? Length 5.5 EV. Oh, EV. And K1 is 2/3 K2 is going to be 5.5 EV. Let's say, oops. Equal to so we're going to have 3 times 5.5 EV, 2 mass electron r squared. We want it the opposite way though. 6 times 5.5 is 33. So 2 pi over lambda. It's lambda 2. We want it, it's going to be equal to K1, which is 2/3 of this. So we actually want, we want the opposite. We want 2/3 of this. So that's going to be 1/2 K1. Hold on a sec. Is right, 3/4 K1 plus 2 here, 1/2. So we're going to times by 2 K1, and K1 is equal to 2 pi over lambda. I can just call this A. So A is equal to 4 times 5.5 is equal to 22 EV times mass of an electron. That's what I would put for that question. this in here. Oh, what's wrong with? Oh no, this is right. This is right. This is my scrap paper. Put any stars here? Okay, here we go. Probability density. Oh, this guy. Well, let's see. Can I figure this one out? What is the shortest time t greater than 0 spatial dependence probability? Oh, right. This is where I was trying to find the common factor here. I think it's En is equal to n squared over 4. I'm pretty sure. So if I'm right, that means E0 it can't be n squared over 4. It must be h bar omega. It must be something like that, right? Right. This is our hydrogen atom, right? Yeah. Do I have the hydrogen? I don't think so. What was it? It was something like n squared. No. I know it was just dependent on n. It was like squared. What was it? It must be something like n plus 1 over 4. Something like this. And if this is the case, then we have 1 over 4. The other one is 1. So this one is going to be contained in this one. So I'm going to guess E2 over H bar. Oops, that's got to be the opposite. H bar over E2. Units. Oh, this guy here. This would be where I put this thing. For a bound state to occur, what's that happening at? That's happening at second bound state. Yeah, I think it's going to be Z naught. Right. That would be my guess for that one. Oh, here we go. Not done this one. And we have let me do it on this paper. All right, and then we want C over D, so we get A over D. We want to get rid of the A's, so A is equal to E to B over what's this one? This one is going to be cosine. No, sine. All right, and let's plug it into the other one here. And A is equal to minus B, A is equal to minus B. So we have equal to this is going to be so those are going to be the same. Actually, it's going to be this plus what's the this is cosine kx, so we have I k c I k x. So go CD plus ikx and this is going to be cosine. So cosine over sine is cotan. Oh, no, they're not that right. Shoot. I'm getting over excited here. This is going to be cosine of kx so we have, I think it's also set of an ik prime. Kx minus ik prime e to the ikx cosine kx x is equal to ik prime minus ikx kx over sine. All right, C over D is therefore equal to this whole mess. X. Oh, oh, these are all supposed to be L. Change L, 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 L. Can I simplify this at all? Yeah, I don't think I'm going to be able to simplify that. So this guy here, what did I do on this one? Oh yeah, I was trying to figure out if there was some trick. You know, the funny thing is I remember doing this problem with operators on my third pass, but I didn't get around to it. Yeah, I think I'll have to leave that one too. All right, well, I'm pretty near the end of the 3 hours I was supposed to devote to it. So I'm going to do what I did with the last ones. This is officially exam done. I'm going to, oh, there's lots of comments now. Oh. Oh, well, thanks, guys. Don't erase the scribbled part. These pencils are super dark. My eraser is garbage, so that's why I'm not erasing a lot of things. I mean, if I were handing in this actual exam, I'd pretty it up a little bit, but there's not even anything to grade here, so this is just purely for my own benefit. So I'm going to go through it and just kind of do what I did. I think it'll be a bit easier than the second midterm where it was a lot of questions where I wasn't sure. So again, this is not kosher what I'm doing here. This is not what I would recommend for getting overconfident for doing an exam if you were to do something like this, because I don't have feedback. I don't know what the actual solutions are to these problems, but I'm going to get a qualitative sense of what kind of questions I felt good on and which questions I didn't feel good on. This is probably not going to give me my actual score, but it could probably define the upper bound for my score, because if I pick the questions where I know I got that wrong, well, then I know I didn't do better than that. So I think I'm going to look at questions that I know I didn't do wrong first to give me my kind of like. So let me go through these things here. So I would say that, what did we have for C was 15 points. There was 5 of them. Okay, well, I got that one probably right. I would say these 3 are questionable. So that would be, let's say, these are, I think this is adds up to 100, right? No, it adds up to 200. So I'm just going to put, for problem 6, I'm just going to put, so it's probably minus 9. Well, there's more points to this question. Hold on a second. Oh, and this one here is almost certainly wrong. This one here is probably okay. So we're probably minus 9, minus 15. So hold on a second. Let me rewrite this one as minus 26. And question 5. Was this one okay? I'm going backwards. Maybe I should go forward. This guy here, I could have gotten it wrong, but it looks okay.